All right, let's talk about fluid mechanics. If you're an engineering student, you know this stuff is literally everywhere. But today, we're going to take one of the most famous classroom demos you've ever seen and really pull it apart to see what's actually going on. You know the one. You hold a piece of paper up to your mouth, blow across the top, and whoosh, it lifts up like it's defying gravity. The big question is, why? Now, you probably think you know the answer, but I'd say stick around. You might be surprised. And here's where it gets really interesting. This quote basically says that the way we usually explain that paper experiment is wrong. So if the classic explanation is out, what's the real one? Well, to get there, we have to start from square one. Yeah, before we can even think about fluids that are moving, we've got to get a solid handle on fluids that are just sitting there. This is the world of fluid statics, and trust me, it's the foundation for everything else. So what exactly is fluid statics? Look, it's the bedrock of fluid mechanics. For any engineer, you have to nail these concepts because everything else we do is going to build right on top of them. At its core, it's just what it sounds like, the study of fluids that are totally still. No motion between the fluid particles. Think about a glass of water just sitting on your desk. That's a perfect example of a static fluid. And since nothing's moving, there's no friction between the different layers of the fluid. The fancy engineering term for this is shearing stress. The layers just aren't sliding past each other, and that actually makes things a whole lot simpler for us. So with no shearing stress to worry about, the only force that's left is the one acting straight on, or normal, to any surface inside the fluid. And that force has a way more common name. We just call it pressure. Pressure is all about how much force you're putting on a certain area. See, it's not just about how hard you push, it's about how focused that push is. This little equation right here, P equals force divided by area, it's one of the most important relationships in all of fluid mechanics. Now, take a look at this diagram. You see all those arrows? They show exactly how pressure works. Notice how they're pushing perpendicularly against every single surface of that little element. Pressure doesn't push sideways. It always pushes straight in, no matter how the surface is angled. And this right here is a golden rule. It's so important. If you could shrink down to a single point inside a fluid, you'd feel the exact same amount of pressure from above, from below, from the sides, from everywhere. It acts equally in all directions. That's a huge takeaway. Okay, so pressure acts equally in all directions. That's a cool fact, but what can we actually do with it? Well, as it turns out, a whole lot. Let's see how this one simple idea lets us build some incredibly powerful machines. This brings us to Pascal's law. Let's break it down. If you've got a fluid in a sealed container, like brake fluid in your car, and you increase the pressure in one spot, that exact same pressure increase happens instantly everywhere else in the fluid. It's like a message that gets sent everywhere at once. And this is where it gets really cool. Think about a hydraulic lift. You apply a pretty small force on a small piston. That creates pressure. Thanks to Pascal's law, that same pressure travels through the fluid to a much bigger piston. Now, because that pressure is acting on a much larger area, bam, you get a massive output force. It's force multiplication, and it's how a person can lift a 2-ton car. And hey, it's not just for lifting heavy stuff. We use these same static principles for making precise measurements. Take manometers, for instance. They're these simple U-shaped tubes that use a column of liquid to measure an unknown pressure. It's all based on these fundamental rules of fluids at rest. Okay, our foundation is built. We've got a good grip on fluids at rest. Now it's time to get things moving and get back to our original mystery. So let's talk about the principle that's at the very heart of all this confusion, Bernoulli's principle. We've all heard this one, right? Fast-moving air means low pressure. It's catchy, it's simple, and as we're about to find out, it's dangerously easy to get wrong. So what's really going on? Bernoulli's principle is actually all about the conservation of energy, but for a fluid. The idea is that as a little bit of fluid moves along its path, what we call a streamline, its total energy stays the same. It can trade pressure energy for kinetic energy, and back again, but the total never changes. A Venturi meter is the perfect textbook example of where Bernoulli's principle does apply. Look here, as the fluid gets squeezed into that narrow section, it has to speed up. To get that extra speed, that kinetic energy, it has to give something up. What does it give up? Pressure. And you can literally see the pressure drop in that middle column of water. That is Bernoulli's principle in action, along a single streamline. Okay, we've got our basics down, we understand pressure, and we understand what Bernoulli's principle is really about. Now, let's go solve this thing once and for all. So here we have it, the showdown. The myth says fast air on top equals low pressure, and the higher pressure from the still air underneath pushes it up. It sounds plausible, it uses the right words, but it's just not right. It's a classic misapplication of the physics. And this quote just nails the problem. Remember how we kept saying Bernoulli's applies along a single streamline? Well, the air you're blowing over the paper and the air that's just sitting under the paper, they are on two totally different streamlines. They're not connected. You just can't use Bernoulli's equation to compare the two. It's like comparing apples and oranges. So what is the real reason? It's actually a team effort of a few different principles. First, there's something called the Coanda effect, which basically says that your breath is going to stick to the curve of the paper and follow it downwards. Now, think back to high school physics, Newton's third law. For every action, there's an equal and opposite reaction. The paper is pushing the air down, so the air pushes the paper up. It's all about changing the air's momentum. That's where the lift comes from. So, what's the big takeaway for all of us here? It's that the simple, easy explanation isn't always the right one. That common Bernoulli story is tempting, for sure, but it's just wrong. The real explanation, with the Coanda effect and Newton's laws, is a bit more complex, but it's also what's actually happening. And honestly, it's way more interesting. You know, this whole thing really shows how a powerful idea like Bernoulli's principle can be twisted and misapplied. And it makes you wonder, right? What other simple explanations have you just accepted as true in your engineering studies? It always pays to dig a little deeper. Thanks so much for joining me.